Thank you for the introduction. Thanks everyone for coming today, and thanks to the meta organizers for inviting me. Um, so, like Jack said, I'm Daniel Varon. I'm a research associate at Harvard, and today I'll be talking about some of the work we've been doing to develop systems for continuous monitoring of methane emissions with satellites. So, as many of you know, there's been a strong interest in satellite observations of atmospheric methane because satellites have routine global coverage. Um, and also a wide array of capabilities for detecting and quantifying methane sources to support policy and methane mitigation. And many of these capabilities are low latency capabilities, or they have high frequency coverage. So, for example, we have satellites that observe the whole world every few days. We have others that are making daily global observations, um, and still others that I'll get to later with even multiple observations per day. And so there are opportunities to use these data sets to build continuous low latency monitoring systems for methane emissions. Um, and so that's what we'll be talking about today. So first, let's look at this current and planned satellite observing system for methane. I'm sure this is not the first time someone has shown this plot in a meta seminar talk, but it's useful to go through some of these instruments to understand our current capabilities and where we're going. So there are two suites of instruments for methane monitoring. One of the area flux mappers, which are designed for global and regional scale analysis. And then there are the point source imagers that can zoom into very high resolution to resolve methane plumes from individual industrial facilities. And the underlying instruments here are all in space. So most of them are active. MethaneSat is the most recent, and it's still in commissioning, but we're expecting to see data from that mission sometime in the next few months. So we can compare these instruments in terms of the magnitude and spatial scale of emissions that they can quantify. The oldest one is GOSAT, which was launched by the Japanese Space Agency in 2009 and is a global surveying mission with relatively coarse spatial resolution so that it mainly provides information at continental scales. The advantages of the GOSAT data set are that it's a pretty long record. It goes back now about 15 years, and the retrievals are very high quality. So these are very well-validated methane retrieval products, and kind of seen as the gold standard for satellite observations of methane at global and continental scales. In 2017, we got a game changer in TROPOMI, which, like GOSAT, has routine global coverage, but it's actually daily global coverage and at a much finer pixel resolution of about 5 by 7 square kilometers. And so this gets us down to the regional scale of, for example, oil and gas basins like the Permian, where in 1 month of TROPOMI observations, we can see clear hotspots over the Midland and Delaware subbasins, which is the centers of oil and gas production in the basin. What TROPOMI can't do is resolve the individual point sources that are giving rise to these regional hotspots. And that's really been the domain of the point source imagers, starting with the target mode instruments like GHGSat, first launched in 2016, Prisma and Nmap and others that are continuing to go up. And so these instruments don't have global coverage in the way that TROPOMI and GOSAT do. So they can observe anywhere in the world, but they have to be tasked to look at individual areas. And the areas that they observe and target can be on the order of 10 or 15 or maybe 30 kilometers across. So relatively small patches of the Earth's surface, but the images are at very high resolution down to about 30 meters. And so with this, these instruments can resolve point source plumes, for example, from oil and gas facilities in Texas or from landfills in India. And there's been a lot of interest in this kind of data product because what it represents is, it basically shows that our observing system can directly identify opportunities to reduce emissions. And we can view this as directly actionable information for mitigation. So there's been a lot of interest in this, this kind of data, and that has motivated some more recent developments in the observing system, which are, not new instruments. They're not designed for methane or any trace gas applications. And these are the broadband land surveying missions, Sentinel-2 and Landsat, and there are several others actually with similar capabilities. But so these instruments are really intended for generalist surface observations. So, looking at land use and land use change and terrestrial resources and things like that. And the data go back to the 1980s, actually the 1970s for Landsat, but what relevant to the 80s is the surprising methane capability of these instruments. So it turns out that we can use these land surveying instruments to map large methane plumes around the world. And the reason is that they have well-placed spectral bands in the shortwave infrared. So this plot is showing in black methane absorption as a function of wavelength in the shortwave infrared. And you can see, notice first that it's a log Y scale. So there's a pretty big range of optical depths, or, it's a measure of absorption. But there are these strong absorption peaks for methane in the shortwave infrared at around 2,300 nanometers and around 1,650 nanometers. And it turns out that the Sentinel-2 and Landsat and other instruments shortwave bands overlap quite neatly with these absorption features. So this is showing, the examples of band 11 and band 12 from Sentinel-2, and in particular, in band 12, we're sampling very strong methane absorption. And so we showed in a paper in 2021 that we can combine these bands in various ways to image large methane point sources globally down to 20-meter resolution every few days, going back to the 1980s with Landsat. And so this has opened up, multiple petabyte scale data sets for methane point sources that are very noisy and so difficult to mine. But there's a lot of ongoing work trying to properly exploit this new class of instruments for methane data. And then the most recent addition to the observing system is MethaneSat. Just was launched earlier this month, and as I mentioned, it's still in the commissioning phase. It's in this chart, it's shown in the area flux mapper category, and I think that that's accurate. But I would also, I kind of feel like this instrument straddles a line between the two categories, because while it's intended mainly for quantifying regional total emissions from hotspots like oil and gas fields, it does this at high spatial resolution, high enough to resolve individual point sources. And so it's kind of a unique mission in that it has joint capabilities between these two categories. Okay, so the first part of my talk will be about a system for continuous weekly monitoring of regional methane emissions that we've been building based on TROPOMI observations. And so TROPOMI is the tropospheric monitoring instrument. I mentioned it was launched in 2017. It sits on the Sentinel-5P satellite, and it makes daily global observations of methane concentration with a pretty high resolution of 5.5 by 7 square kilometer in the nadir configuration. This is a really, really dense global data set. This is a map of mean TROPOMI observations for 2019 globally. There's more than 50 million data points that are aggregated in this plot, and you can see it's very rich and very dense. There are immediately these large point sources, sorry, not point sources, but hotspots that catch the eye, at least for me. I mean, signs of very large emissions in China and India, from the Sud wetlands in South Sudan, from across Nigeria, from the Permian Basin in Texas and New Mexico, and from the California Central Valley, just to name a few. And there's been really strong interest in using TROPOMI to quantify these hotspots in terms of the magnitude and variability of emissions and to understand what is driving them. So how do you do that? Well, there are different approaches, but the state of the art is what we refer to as atmospheric methane inversion. And at Harvard, we've been developing tools to do regional methane inversions based on satellite observations, and particularly based on TROPOMI. It really boils down to an approach to improve a prior estimate of methane emissions, which often comes from a bottom-up inventory, like the gridded version of the EPA greenhouse gas inventory in this example for the Permian. Although actually within the Permian here, I'm showing the Environmental Defense Fund's EIME inventory. But in any case, in this inversion, we're trying to improve a bottom-up inventory using Bayesian statistics on the basis of the satellite observations. And the way this works is we start with a gridded estimate of emissions, which we call X, and the example here is for the Permian Basin and surroundings. It's combining the gridded version of the EPA inventory outside the Permian and the EDF inventory inside the Permian. We plug this into an atmospheric transport model to predict what TROPOMI might observe, if it were observing the simulated atmosphere. And our transport model of choice is GeosChem. And then we compare the predicted concentrations with the actual observed concentrations, and the inversion consists in that comparison. So we're adjusting the emissions up and down to get a better match between the observations and the model. And once we found an optimal match, we have obtained our posterior estimate of emissions. So this is the improved estimate of, or the improved version of the bottom-up inventory that we start with. And the way this works formally is that we minimize a cost function J that looks like this. I won't go into each term, but basically there are two important expressions. So there's this expression on the left, and this penalizes the inversion from departing too far from the prior emission estimate. And then the expression on the right penalizes the inversion for differences or model, between the model and the observation. So this penalizes the inversion for model data mismatch. And in 2022, we released an open access cloud computing facility for doing these atmospheric methane inversions that's available on the AWS cloud. It's called the Integrated Methane Inversion, or IMI, and we're currently on version 1.2. And Lucas Estrada, who introduced himself, before the talk, has been a lead developer on this project. And so the way it works is that it's designed for researchers and stakeholders to be able to run their own TROPOMI inversions at 25-kilometer resolution for any region and period of interest compatible with the TROPOMI record. So the example here is for the Permian Basin, where we have this irregular region of interest across the basin. But actually, the simplest implementation is to use just the latitude and longitude bounds of a rectangle. It can be that simple. You have a start date, an end date, and then latitude and longitude bounds of a rectangle, and you can run an inversion at 25-kilometer resolution for that with one command. So the way it works, the first step is what we call the IMI preview, and this is a feature that we developed because we didn't want users to configure an inversion, that maybe is not very well configured. For example, it could be a high resolution inversion for Russia, in the wintertime when there's no observations. And then commit to running that inversion without realizing the weakness of the configuration. That could be pretty expensive, when you're running on the cloud. Our software, of course, is free, but if you want to run anything on AWS, you have to pay for it. So we implemented this feature to allow users to preview what they can expect from their inversion before actually committing to running it. And it shows the user a variety of different things. The TROPOMI observations that are available on the cloud. This is for a 1-month inversion for the Permian, as an example. The prior emission estimates to be used in the inversion. And then also the observation density and shortwave infrared albedo, so that users can diagnose potential gaps in coverage or observation, retrieval artifacts that might negatively impact the inversion. Critically, it also estimates the information content of the inversion as configured, and it does this through a quantity called the degrees of freedom for signal, or DOFs. And this is a measure of information content. It represents the number of pieces of information that can be constrained in the inversion, and a practical minimum to quantify, a regional total emission in an inversion is somewhere around 0.5 or 1. So in this case, we have tons of data for the Permian Basin, more than 20 or around 20,000 observations within this region of interest. And so we have an estimated DOFs of 12. This is more than enough. Once the user is satisfied with the inversion, they can submit the job. It's a single command, and it will output a variety of different fields of interest. So the posterior emission estimates first and foremost, but also posterior over prior ratios and average incremental sensitivities. You might be wondering what those are. This is another measure of information content. And in particular, if you sum up all of these values across the inversion domain, you get the degrees of freedom for signal. And so in this case, we found from our inversion, the true value of DOFs was about 11. We expected around 12. That's a pretty good match. And there's been a lot of interest in this tool. We currently have more than 50 users across more than 10 countries and 20 plus interested organizations. So if you're interested in running methane inversions or exploring what this software is capable of, I'd encourage you to check out our website. We have lots of documentation, and we're also responsive to emails if you're curious about how this might apply to your use case. Now, I'll say a little bit more about how all of this works behind the scenes. So this is a software tool on AWS, and it uses two key AWS services. So one is the Elastic Compute Cloud, or EC2, which is the main computing service. And the other is the Simple Storage Service, or S3, which is AWS's main service for data storage. And so the user interacts with the IMI through an EC2 instance, and in particular through what's called an Amazon Machine Image, or an AMI. So we've made one of these for the IMI, and what it represents is basically a canned software environment. So normally when you set up one of these complex models, if you're trying to do this locally, it's a big pain to set up all of the various software dependencies to get the thing to run. But when you use an Amazon Machine Image, everything comes ready to go. So you can just open up the configuration file on the machine image, put in your configuration, and run it, everything out of the box, and it'll run. So yeah, user mainly interacts with this configuration file. The first step is this preview feature. It can be skipped if you know for sure that your inversion is going to work. And then ultimately everything gets sent through our IMI workflow to produce the optimized methane emission map. Now, along the way, the IMI automatically draws on data resources in S3. And so these are things like the TROPOMI observations, which are maintained in an S3 bucket, the default prior emission inventories that we provide for users, although there's also option to use custom inventories as prior estimate. The GEOS meteorological data that we use to drive our GEOS Chem transport model simulations, and then the boundary conditions for methane that we need for our regional inversions. We need to have boundary conditions at the edges of the region of interest. And so, all of this is described in a paper I wrote in 2022, but it was really an effort to make use of existing AWS resources. So all of this stuff, including GEOS Chem, was already on the cloud, and we kind of just saw an opportunity to put all of this together into a software product that would be useful to the public. And then very quickly, this is what the basic IMI configuration file looks like. I'm not going to go through all these different options, but in the simplest case, you can just set a run name, a start date, and an end date for an inversion, and then the longitude and latitude bounds of a rectangular domain, and that's enough. Okay, so back to the theme of continuous emission monitoring. We're getting ready to release IMI 2.0 in the next 2 or 3 months. And one of the flagship new features in 2.0 is a Kalman filter option for continuous emission monitoring. And the goal is to enable users to perform continuous low latency monitoring of methane emissions with TROPOMI and the IMI. And so this diagram illustrates sort of how the process works, and it's assuming an example of weekly methane inversions for the Permian Basin. So in a week K, we started with initial conditions and prior emissions for methane in the Permian. We use those to run a 1-week inversion based on TROPOMI observations, and this gives us our posterior optimized methane emission estimates for that week. We then plug those back into the model to run a 1-week simulation. That gives us initial conditions for the next week. And we also send the posterior back to serve as the prior estimate for the next week. And so we do this iteratively. And this is sort of what the result looks like in action. This is for the Permian Basin, where we have done 127 consecutive weekly methane inversions from mid-2018 to end of 2020. This is showing on the top left here a typical week of TROPOMI observations. It's about 3,000 to 4,000 observations within the bounds of the basin. And then on the bottom right, the results of all of those inversions. So the weekly values are the black points, and then the red lines are showing 4-week moving averages of the weekly estimates. And so what we get out of this is pretty strong and interesting variability, particularly on multi-week and 2 or 3 month scales. So the low frequency variability over this 2-year period is actually quite weak. It's the emissions are kind of flat, but on multi-week scales we see these big swings, sometimes by almost a factor of 2, up or down. And so in this paper in 2023, we tried to validate and interpret this variability, and we ended up finding that the main drivers seem to be new well development and trends in natural gas price. And so this is taking a closer look at this here. So the plot on the right is showing at the top those weekly methane emission estimates, and then a variety of potential explanatory variables for what might be driving the variability that we see in emissions. Things like oil and gas production, new well development, pipeline takeaway capacity and outflows, VEERS flaring activity, and data for oil and gas price, including the local Waha hub natural gas spot price. That's in black here. We did a multilinear regression analysis, and we ended up finding that, first of all, oil and gas production is not a good predictor of methane emissions. So we saw that over this period, there was about a 50% increase in oil and gas production, but we didn't see anything like that in emissions. The emissions are pretty flat over the period. So I'll come back to that in a minute. The really important statistically significant drivers turned out to be new well development and the local gas price. So we'll start with new well development. There are these two periods that are pretty informative. So one is at the end of 2019, there's a big spike in new well development in the Permian from about 500 new wells coming online per month to more than 1,200. And then again in early 2020. So for those two spikes, we see a corresponding surge in methane emissions over that month, and that remains elevated for the month afterwards before falling back off, which is sort of to be expected because of the expectation of higher emissions from new wells in the first few weeks or a couple of months after production commences. Then there was this COVID-related slump in new well development, and it's during that period, starting a couple of months after the slump in development, that we see our lowest emission estimates. The other, really important driver seems to be the local gas price, and particularly during this period in early 2019, we saw a major crash in the local gas price into negative price territory. I believe something like this is happening now or recently in the Permian Basin again. And during this time, at least, I haven't looked at the recent trends, but in 2019, we saw a corresponding uptick in emissions. So there was this anti-correlation that seemed to arise during this period between emissions and the local gas price. And so our interpretation of that was that there might be less marketing of by-produced gas during periods of really unfavorable local gas price. Now, all that said, with this multilinear regression, we could only explain between a third and a half of the variability that we inferred from TROPOMI. And so there must be other factors at play as well. Now, something else we can do with this kind of continuous monitoring framework is we can look at trends in methane intensity. So that's defined as the methane emitted over the methane gas produced in a basin. And so here we saw, a mean intensity over the period of around 4.5% and a bit higher in the New Mexico Permian Basin, which might have something to do with the lower producing wells there, as we saw in a recent paper by Mark O'Mara from EDF. But the really interesting thing is that we have this decreasing trend in intensity of about 1% per year, from around 5 to 6% in 2018 to 3 to 4% in 2020. And so that would indicate some improvements in operator practices, or at least increased marketing of gas. And it's consistent with this finding that emissions stayed relatively constant despite a major increase in production. But all that said, the intensity, at least during this period, is still an order of magnitude higher than the industry target of about 0.2%. So there's more work to be done. Okay, now all of this motivates a vision for a more operational continuous emission monitoring system, something that we can just have running all the time for different regions of interest, so we can keep track of what's going on in terms of methane emissions and maybe methane intensity as well. So this is our vision for what that might look like. We start with a triggering event. That could be something simple, like it's Monday morning. We want to run some inversions before people get into the office. That event leads to an IMI container being deployed automatically on AWS. This runs the inversion automatically, and the results are pushed to S3 for long-term storage and for analysts to go and look at. And then for the next triggering event, there are also the most recent posterior estimates that can be accessed from S3 to serve as prior. And so that's what this is sort of an illustration of what that might look like in practice for 5 oil and gas basins, in the orbit of Texas. So the Permian, Anadarko, Barnett, Eagle Ford, and Haynesville. And we're still digging into this variability. Some things that are immediately apparent are that, at least for the Permian, we seem to have a seasonal trend here with lower emissions in the summer than in the winter. I think others have observed this trend with independent observations. I'm not really sure, what the explanation is. I've heard different hypotheses. One could be that, there is some infrastructure problems that result from low temperatures in the winter. Another is that maybe gas demand just varies seasonally, and that can explain the seasonal difference in how much by-produced gas gets marketed, and therefore what the methane emissions end up looking like. So if anyone has thoughts on that, I'd be glad to hear them. We don't see such an obvious seasonal trend in the other basins, but what we do see pretty much across the board is that the emissions are either flat or slowly decreasing. And this is despite an increase in production everywhere except for the Barnett during this 2-year period. It's 2022 and 2023. So that indicates that, even as recently as a few months ago, these oil and gas basins seem to be showing a decreasing trend in methane intensity. And then finally, when I produced this plot, we were 2 weeks into January 2024. And so that represented a latency of about 2 or 3 weeks since this goes to, the very end of 2023. And so that's where we're at right now. We have a latency for this kind of work of, I'd say 2 to 4 weeks. But we're working on cutting that down to a few days so that we can really have an operational, automatic, cloud-based monitoring system for regional methane emissions from oil and gas basins and other areas of interest. So, okay, one of the first things that we need to do is validate these results and get a sense of, how realistic they are. The ultimate goal is to apply this framework kind of, to many different areas around the world. And so before we do that, we should validate our results in the US, where we have a lot of instrumentation and a lot of data. And so, the first thing that we can look at is the spatial distribution and temporal evolution of emissions in the inversion. So this is a map of the posterior emissions that I'm getting from my weekly estimates for the Permian. And it shows, the emissions seem to move around the basin quite a bit, but are mostly confined to those 2 hotspots around the Midland and Delaware. So this is a first sanity check, but we can obviously be much more rigorous in our validation. I'll pause this. And the best way to do this is by comparing our inversion results with independent measurements. And in the Permian, we're lucky to have a long data record from Penn State University's Permian Tower Network, which is run by Natasha Miles, Scott Richardson, Zach Barkley, and Ken Davis at PSU. And this map is just from their website, and it's showing with these yellow stars that I've overlaid the positions of 5 of their towers, and this is a picture of what one of them looks like. And so they're most, kind of stationed around the Delaware. And so what we can do is we can compare our inversion results with the measurements of methane concentration at those towers. So there are a lot of plots here, but it's simpler than it looks. Each plot is showing on the y-axis the geoschem predicted methane concentration at the location of a tower, and on the x-axis, the actual measurement at that tower. And the columns correspond to different towers. So there are 5 columns here for those 5 different towers I showed. And then the top row is showing what that comparison looks like when we're using our prior estimate of methane emissions for the Permian. And you can see that geoschem systematically underestimates the concentration at all of the towers. The emissions are too low. The bottom row is showing the same thing, but using our posterior emission estimates. So this is after running our weekly inversions. And you can see that there's a much better match between geoschem and the towers. It's still not perfect. In particular, we have this persistent bias, low bias in geoschem. And we think this has to do with the different definitions of the background methane concentration as seen by the satellite and modeled in geoschem, and between that and what's seen by the tower. So we're still looking into that. Then the difference in slope, for example, for this tower, where the slope is less than 1, might be what we call a representation error, basically a limitation of our model, which has 25-kilometer resolution to capture very high concentration gradients that might be seen at a point location by a tower. Anyway, across the board, what we're seeing is that our inversions are dramatically improving the fit with the tower observations in terms of R-squared, RMSE, and bias. We can also compare our weekly estimates with independent estimates from other groups. And so this is comparing with some tower inversion results from Zach Barkley at PSU. So, my estimates are shown in black and green based on TROPOMI. This is all for the Delaware Basin in particular. And then Zach's tower estimates are shown in gray. And what you can see is that, first off, the satellite is biased high relative to the tower. So we're, about our emission estimate for the Delaware is about 25% higher than what Zach's getting from the towers. But the seasonal variability looks pretty consistent. We have a low in the latter half of the year, and we have a high in the early part of the year for both 2022 and 2023. Okay, so we have some confidence, and this is still a work in progress, still preliminary results. I'm also working on validation efforts for the other U.S. oil and gas basins, but we're starting to build pretty good confidence in our methane inversion results for those U.S. regions of interest. And this now motivates applying this continuous monitoring framework outside of the U.S. and to areas where there may be less readily available data for validation. And one of the first focus areas we've chosen is Turkmenistan, which is well known as a global methane hotspot, particularly from oil and gas. This background image is showing super emitter detections by TROPOMI for the year 2023 that are reported by the Esron Netherlands Institute for Space Research. And you can see lots of very large plumes detected by TROPOMI in the western part of the country and the eastern part where there's a lot of oil and gas production. Now, at the same time, since 2019, when GHGSat discovered extreme emissions from oil and gas infrastructure in Turkmenistan, there have been some diplomatic efforts to help Turkmenistan reduce its methane emissions from oil and gas. And these are ongoing, recently taken up by the Biden administration. And so there's been a lot of interest here because these oil and gas emissions are kind of seen as a low-hanging fruit in fighting climate change. So we have basically kicked off a project to do continuous weekly methane emission monitoring for Turkmenistan. First of all, to get a sense of what the national total emissions are like and how they're changing over time. And second, to be able to look for any signal of decreasing emissions. The hope is that these diplomatic efforts will be successful and we'll get a win and lower emissions from Turkmen oil and gas infrastructure. So we want to be ready to see that as it occurs. And so the first step has been to do several years of weekly methane inversions. And so this is the result, it's still a recent and preliminary result for the years 2020 through 2023, where the red dots are showing the results of my weekly inversions, and then the thick lines are different moving averages. I'm getting a mean emission from across Turkmenistan of around 6 teragrams per year. Very interesting temporal variability during this period. There seem to be 2 regimes of variability. So in the first half of the period, from early 2020 through mid 2021, it seems like emissions are kind of just marching upwards steadily. And then following the summer of 2021, it looks like there's a seasonal variability that takes effect. And the seasonal variability, interestingly, is opposite what we saw for the Permian. So here there's higher emissions in the summer than during the winter. So any thoughts about that? I'd love to hear them. I'm not really sure what would drive it, but an interesting finding, I would say. And then we can aggregate those weekly results at the national level, and we can also break them down into some of the different responsible sectors. So this plot over here is showing the national total methane emissions from Turkmenistan. The orange line are the median of the weekly values for the year, and then the box plots are showing the interquartile ranges. So you get a sense of the variability, within the year. And the national total, as I said, is around 6 teragrams per year, and the contribution from oil and gas is about 2/3 of that, about 4 teragrams per year. And we found that it's responsible for almost all of the temporal variability that we're seeing in emissions from Turkmenistan. Okay, so that's the first part of my talk. The second part, I'd like to look at a very different form of continuous methane emission monitoring, and this is continuous staring from geostationary orbit to detect and quantify very large transient methane releases. And, so these are the results of a recent paper by my former student, Mark Watine, who's now at IMEO, where we showed how GOES, which is NOAA's Geostationary Operational Environmental Satellites, is the US operational weather satellite system that's been in space since the 1970s, can detect very large methane point sources. Despite having a relatively coarse 2-kilometer pixel resolution in its SWIR bands, shortwave infrared bands, and with the unique capability of scanning the Americas every 5 to 10 minutes. So this is a very temporally dense data set. So let's go back to this methane observing system plot. A major gap in this observing system is temporal coverage. And I know that's kind of contrary to what I've been saying for the past 30 minutes or so, which is that we have, frequent observations and we can do continuous monitoring. But, if you dig into it a little deeper, so I've been talking about continuous monitoring at weekly scales or maybe monthly scales, things like that for large regions. But all of these instruments, including TROPOMI, are in low Earth orbit. So they observe at most once per day. Often it's longer than that. It could be a few days. It could be more than a week, depending on the instrument for a given location on Earth. And the instruments are almost all in either a morning orbit or an afternoon orbit, so that they observe around 10 a.m. or 1 p.m. So for most of the day, we actually don't have any coverage. And so that means that when we see a methane plume, one of these point source plumes, we don't actually know how long it lasted, what was the total duration, therefore the total impact. And the solution to this problem is continuous staring from geostationary orbit, but our only geostationary mission in geocarb has been canceled. And so this is really what motivated our look into what we could do with the current geostationary assets, excuse me, like GOES. Now, this is the scanning configuration of GOES. It's a video. Let's see if it loads. Yes, I'll skip ahead a little bit. So GOES is observing the full disk over the Americas every 10 minutes. But it also has a scan mode for CONUS, the contiguous United States. That was just shown there, which it observes every 5 minutes. And that includes part of Canada and part of Mexico as well. So, okay, we don't have to go through this whole video, but it gives you a sense of how this whole disk is going to be covered every 10 minutes all day long from geostationary orbit. And GOES, why does GOES have a methane capability? It's a weather satellite, certainly not intended for observing methane in the atmosphere. But it's for the same reason as those broadband land imagers, Sentinel-2 and Landsat. It has these well-situated shortwave infrared bands. Now, I said that GOES first went up in the 1970s. Unfortunately, the shortwave infrared band was only introduced in 2016, I believe. So we can't go all the way back in time like we could with Landsat. But starting in 2016, we do have this capability. So this is showing, this plot on the left here is showing methane absorption now as an absorption cross-section rather than an optical depth like I showed before, as a function of wavelength. And it's showing in green GOES shortwave infrared bands, so band 5 and band 6. And band 6 in particular samples strong methane absorption. Now you'll notice that if we were to widen this band to the right or shift it to the right, it could significantly improve the methane sensitivity. And that's something that we're actively looking into for any potential future geostationary missions. And this band configuration gives us the ability to perform methane retrievals just like we do for Sentinel-2 and Landsat, but every 5 to 10 minutes. Now, I mentioned that we have 2-kilometer pixels here. This is much coarser than, for example, Sentinel-2 pixels are 20 meters. So this is much coarser, and it means that we're limited to seeing very, very large releases. But we can see them essentially in real time. And the GOES data from 1 minute or 2 minutes ago are currently downloadable online, and we can make movies of these very large releases. So this is an example. This is the first one that Mark discovered when he was working on this back in 2023. He started from this TROPOMI snapshot of a big methane cloud, that was detected downwind of an oil and gas pipeline in Mexico. And this is a pipe, it's called the El Encino La Laguna, or EO pipeline, that carries Permian gas to Mexican markets. And so in May 2019, TROPOMI observed this big methane cloud downwind of the pipeline. And we went back and had a look with Sentinel-2 the day before, and it looks like they were doing a release from a pipeline block valve station the day before on May 11th. And this is a massive release. I mean, we're talking hundreds of tons of methane per hour, but a transient source. So, might only be active for an hour or 2 or 3 hours. And these block valve stations, many of you will know better than I, that these are, pieces of infrastructure that basically segment pipelines. So if there's a maintenance event, you can open or close those valves to, empty or seal a segment of a pipeline. And so, yeah, with GOES, we can see the 5-minute evolution of this large release. It was a 3-hour release on May 12th, 2019. TROPOMI observed it downwind a few hours after, or can't remember exactly now, maybe it was an hour after it happened. No, a few hours, yeah. This is at 2020 UTC, and it starts at around 1700 UTC. And the total release was more than 1,000 tons over those 3 hours. Interestingly, something we can do with these geostationary very, very high frequency measurements is that we can quantify the variable source rate. Since we don't just have one snapshot of the plume, we can actually see how it evolves over time. And so this plot on the left is showing in red how the total methane mass in the plume increases over time. So, when the release starts, there's no methane in the plume. And then as the release progresses, more and more methane is released into the atmosphere, and the plume gets bigger and bigger. And from this, we can do a sort of differential analysis, the change in the methane plume mass over time, to estimate the emission rate. So that's shown in blue here. And if we integrate the area under that curve, we get the total release mass. And so we find that the emission rate ranged from 250 to 550 tons per hour during that 3-hour period. And this really, it illustrates how these geostationary measurements can be used to quantify changing source rates from these transient releases and the total release duration and mass for these very large events. Another really neat example that Mark found is the double plume release from a pipeline in Indiana. And so this is a neat one because it was observed by TROPOMI a few hours after the fact back in June 2020. And it was kind of mystifying at the time because the apparent plume origin, is for both of these clouds, pretty much somewhere in Illinois. And there's really nothing at those locations that could explain such large releases. And so with GOES, we can trace back these detached plumes to their source along the pipeline. And so this illustrates how continuous staring from geostationary orbit can enable better source localization and monitoring of these transient releases. And in this case, again, the culprits were these block valve stations along the pipeline. Finally, we wanted to see if we could do independent plume detection with GOES. And so Mark went through 2 months of snapshots over the Permian Basin, a 100 by 100 square kilometer subregion of the Permian. And he just poured over every 5-minute snapshot until he found something. And here it is. It's a pretty weak signal, but what we find is that it was about 60 tons released over 20 minutes. No other satellite, passed during this time to observe it. That implies a release rate of 170 tons per hour. Again, this is a massive release. But we had a closer look. We said, okay, the signal to noise ratio inside the plume versus out is around 5. Our 10-meter wind speed at the time was about 5 meters per second, which is pretty moderate. And the scene in the Permian was moderately complex. So, from that, we inferred a minimum detection limit. If the stars align and we have really low winds and a really clean scene, what's the smallest source we could see, if we were lucky? And we said, okay, it's got to be somewhere below 100 tons per hour. And this is something that we're still looking into to better characterize the GOES plume detection limit. And then finally, there's a lot of room for future work here. GOES is not the only system with this methane capability. Europe has recently launched the Meteosat third generation, or MTG system, which covers Africa, Middle East, and Europe. And then Japan has been operating Himawari 8 over much of Asia and Oceania since 2014. So there's there's potential for a global georing for continuously monitoring very large methane releases with these weather satellites. And with that, I'll stop and take any questions. Thank you for your attention.